All right, section 1.5 is going to finish our chapter 1. So what that means is coming up is that the next class period we're going to do a review in class. If you want to, prior to that, start working on the review inside of WebAssign, you're certainly welcome to. It's open and available to start working on. It is lengthy, it is extra credit, so you don't have to do it necessarily, and you certainly don't have to do all of it. But for whatever amount of it would be helpful to you in preparation, I want it to be there for you, and you do get a percentage of points out of 5. So if you completed it completely, you'd get 5 points. And if it helps you to think about that, you can kind of think about it like being 5 points added onto a test grade. Points are points, so it doesn't really matter, but it's not WebAssign points, which are a little bit fuzzy. I also sent you an email, or put a Canvas announcement in about WebAssign. I don't want to say it on the video because hopefully at some point this will not be true in some future semester, but make sure and look at that WebAssign comment if you haven't looked at it already. We're going to continue doing what we've been doing with WebAssign so far. All right, so we'll review next class period, and today will be our last section of new material, and then our test will be 2 class periods from now. So for us this semester, that will be next Wednesday. All right, so keep that in mind. You'll be getting probably by Monday, maybe not by class Monday, you'll be getting an announcement telling you that there will be a review session and when and where it will be, and possibly with whom is going to be leading that review session for the test too. All right, so as we take a look at this section, I want to first define what an infinite limit is. I do hope that you have things printed out because you're not going to want to write all this down. So if you don't have printout notes for this, you might just push pause in your mind and just read through this and stick with us, and then print them out later because it is kind of lengthy on some of the typing pieces today. So an infinite limit. So we're going to let f be a function that is defined at every real number in some open interval containing c, except possibly at c itself. So we've got something that we can plug a number in for everywhere except for c. Maybe we can't at c. Maybe we can, but maybe we can't. The statement that the limit as x approaches c of f of x equals infinity means that for every m greater than 0, there exists a delta greater than 0, such that f of x is greater than m whenever 0 is less than x minus c absolute value is less than delta. And a similar statement can be made for each n less than 0. First of all, this should feel like something you've seen before, does it? It feels like the epsilon delta description that we had before. And it is quite similar. Let me show you a picture of what it's describing, though, because I think that might make it a little bit more helpful than just the language. So imagine, and this isn't, of course, the only graph you could draw, but I need an arbitrary graph, so this is the one that I'm going to pick. Imagine you had a graph that looked something like this. And it's defined everywhere except that asymptote spot, right? Like I can't put that in, and that's what they're calling c right here, so we'll call it c down here. Everywhere else, I have function values, no problem. Okay? So what this is describing is that if you have a value m greater than 0, so it's up here somewhere, and it says at the end we can also do n less than 0, so we could do the same picture just flipped upside down if we wanted to, and n would be beneath the x-axis, okay? So the m is greater than 0. Then if we were able to take a value close enough here, then we would end up having the space up here where we would be above m. There would be space where we would exceed the value that I've capped out at m. Okay? So these values here, this one down here, they're describing as epsilon. My pen. This distance between c to this little bracketing that I've done is epsilon in each direction. And this distance right here, I'm sorry, I wrote the wrong one. It's delta down there. I apologize. Notation's not where I want it to be. It's delta down here. So if we can get close enough to c, we will exceed the value m for any m. And that's the important part. It says for any m. So, okay, I don't like that m. I just make the m bigger. Okay, well, we're going to get bigger. It just means that around the c value, I need to get tighter. And if I get it tighter around the c value, I'll be above that new m value too. And I can do that forever. And as long as I have the ability to do that forever, what we would say is that this limit is infinity. Now, it's really not great to say that the limit is infinity. The limit doesn't exist, all right? Limits are numerical values, and infinity is not a numerical value. It's a concept. It's a concept that says that we get something bigger every time, right? So it's not that we're really saying that it exists in its infinity. What we're saying is we're saying how it fails to exist. It fails to exist because it gets infinitely large. So when we proclaim that the limit is infinity, what we're really saying is it's so big that there's no cap and it's always getting bigger. Infinity is not a number, okay? So we can't really treat it like a number. It fails to exist. It fails to exist here because it's infinitely large. And that's not the only way something can fail to exist, right? It can fail to exist because there's a hole, right, with a jump. That's one option. Or even just a jump in the graph with holes on each end. So if there's jumps in the graph, it fails to exist too. So knowing that the limit is infinity tells us it fails to exist, but I understand more why. I know that there's an asymptote there that's causing this, as opposed to, say, a jump in the graph. There's a note on this that you need to be careful of. Be sure that you see that the equal sign in the statement does not mean the limit exists. This is what I was talking about. On the contrary, it tells you how the limit fails to exist. By denoting the unbounded behavior, unbounded means there's no cap. That's what we're saying. M can't be the biggest number. There's something always bigger as x approaches c. So that's what this note is in your notes for, is to remind you of the fact that the limit doesn't really equal infinity. It's just telling us how it fails to exist. So we're going to do some examples of this. Here's our first one. It says to determine whether f of x approaches infinity or negative infinity as x approaches 4 from the left and from the right. So there's two pieces that we're working on. It tells us that we're going to do the limit as x approaches 4 from the left, we'll go in order, of this function, which is, I'll just write it in here, negative 1 over x minus 4. And then the limit as x approaches 4 from the right of negative 1 over x minus 4. Now, in our last section of material in 1.4, we talked about the fact that if we can simply plug the number in, we're good to go. By the very nature of this section, that's not going to be able to happen. We're going to get infinities or negative infinities, which means that when I try to plug in 4 into this, I'm not going to get that working out for me. I have a constant on top, I have 0 on the bottom, right? So I need to figure out what I need to do when I don't have the ability to plug it in. Well, that puts us back at the other two ways of doing limits. One of them was with a graph, and one of them was with a table, right? I'm going to do a graph on this one because I'm going to do a table on another one, all right? But they're both viable options here. I can either create a table that represents each of these pieces, right? One that shows the 4 values coming from the left, so that means the value is slightly little smaller than 4, right? Like 3.9. Values coming from the right, slightly bigger than 4, like 4.1. I'm going to do a graph because I want you to see how that works as well as a reminder. So if we were to draw this graph, and you can get it from your calculator, I'm not asking you to remember how to do it per se. I mean, like, that's not the point right now. But if I were to put this into my calculator, it would look something like this. My calculator's not going to do a dotted line, but I'm going to draw it in. The graph looks like this. Your calculator might actually try to connect it and make it a vertical line in between. You have to use the knowledge that you have to say, I know that that's not really what's happening here, even though the calculator's doing that. All right, so this value that I've marked here with the dotted line is at 4. There is an asymptote there. It is discontinuous there. Those are all things we did in the last section. What this is asking me to do is asking me to take a look at 4 from the left. Well, this is the left-hand side of 4. It's over here. So I'm moving toward my dotted line, my asymptote from the left-hand side. I'm moving like this. And as I do that, what types of numbers am I getting? Am I getting infinitely big numbers, like positive infinity, or infinitely small, like negative infinity? They're bigger. They're going up. They're going up. Yeah, so this is the part of the graph that I should be looking at on the left-hand side. Okay? So it's shooting up to infinity, right? So what that tells us over here is that we're going to write that this is infinity. On the other one, I'm approaching from the right side. We'll change colors. I'll do green. So this is the right side. So if I'm approaching from the right side, and I'm going to have to be tracing along my graph, and by graph I mean the curve that it sketches, not the axes. The axes is just a reference point. It's not really the graph. The graph is this piece. So as I'm going along here, what's happening to these values down here? They're getting infinitely small. And infinitely small is negative infinity. So these are the answers to the question. And I recognize that you can just look in your calculator to do the graph. But since I can't see the calculator, right, because I'm grading your paper later, either from a quiz or, or a test or something like that, you have to draw the graph for me. And you have to show me what it is you're looking at. Whether it's arrows that indicate the direction of things going, or whether it's these circles that are indicating where you're sort of projecting your ending up, something that indicates which part of the graph that's of value that you're looking at for your answers. Does that make sense? So this is the work that you would show if you were showing a graph for something like this problem. I have a tickle in my throat today that just will not go away, so I'm sorry if I keep coughing. It's because that tickle just is causing me issues. All right, we talked about vertical asymptotes last time, so we're going to talk about them a little more today. If f approaches infinity or negative infinity, like we had in our last example, as x approaches c from the left or from the right, then we call this line x equals c a vertical asymptote of the graph. So on the last one that we did, this line, x equals 4, was a vertical asymptote. Now, vertical asymptotes have some features that we're going to look at. So we're going to consider letting f and g be continuous functions on an open interval containing c, and f of c not equal to 0. G of c does equal 0. Then there exists an open interval containing c such that g of x does not equal 0 for all x not equal to c in the interval. Then the graph of the function h of x equals f of x over g of x has a vertical asymptote at x equals c. So what this is saying is that this piece right here, if I plug c in, will be 0. But the numerator won't. So whatever the functions are, if I plug the c value in, whatever c value I'm considering, the last problem was 4. If I plug in the number 4, let's say, the numerator is not 0 and the denominator is. And when that happens, we get a vertical asymptote. So this is just a more broad kind of a description than what we just saw over here. This is describing what it's called, and this is describing how it happens. So when we're looking for vertical asymptotes, we're doing a lot of the same things we've already been doing. We're looking to see where the denominator equals 0. We might be looking to see if we can factor anything, right? Like on the last example, there's no factoring. There's not a very exciting function going on here to factor with. But on the next example, we have the potential that maybe it will, because there's more going on. So what we're looking at when we're looking at this equation is we're looking at factoring to see where the denominator equals 0. And you have to be a little bit careful because there was a condition over here that I mentioned. The condition was that the numerator can't be 0, but the denominator is. So just looking at where the denominator equals 0 isn't enough. Okay, we have to look at where the numerator potentially has places of equaling 0 as well. So on this function, we are going to start by factoring. And in doing that, we need to factor the numerator and the denominator, because I got to figure out where the denominator is 0 and the numerator is not. So how will the numerator factor?
X minus 3 and x plus 3.
Right. So this is a difference of squares. Do you guys remember that? It's a difference of squares formula. And the denominator also will factor, but it's not a difference of squares. because it's a trinomial. So how will the denominator factor?
X.
Okay, so this is what we were doing in the last section. We were just doing it for the purpose of answering a different question, right? About continuity. But the answers about continuity really are just saying the same sorts of things about asymptotes and wholes. Remember? So what do you notice happens between the numerator and the denominator here?
The x minus 3 cancels out.
Yeah, the x minus 3 is canceling out. What does that create, or what is that proving is part of your graph when it happens? It's removable. So this is telling you it's removable. And it's also telling you graphically that there's a hole in the graph, right? So the reason I don't have an asymptote here is because if I were to put 3 in, right, x equal to 3, it would make the denominator to 0. Like, that's part of what this says over here. But it also makes the numerator 0. And if it makes the numerator 0, it doesn't fit into this description, does it? So that's why we've got to look at the numerator and the denominator. However, this piece gives me an x value equal to what?
-1.
-1. So if I put in -1, the denominator will be 0. And if I put -1 in the numerator, it's not 0. And you can think about putting -1 into the numerator of the reduced piece that has the x plus 3, or the original piece, x squared minus 9. It won't matter. If I put in -1, I'm still not going to get 0 on top. So right here at x equal 1, this is my vertical asymptote. You notice the work doesn't look any different hardly than what we did in the last section, right? We're not introducing new work. We're introducing a new idea about how to answer a different kind of question that's being asked. Okay, let's do another one. We're going to determine whether the graph has a vertical asymptote or a removable discontinuity, much like the questions before, and from the last section, in fact. And it specifically asks us at the point x equal -1. So on this one, if I were to attempt to try and factor like I did here, what's going to happen?
You're going to be left with x minus 1.
Are you? The denominator won't factor because it's linear. Does the numerator factor?
Yeah. No.
Okay, so you're right, the answer is no. So you might be tempted to think it looks kind of like the numerator over here. What's different between these two numerators?
It's negative signs of squares.
Yeah, it's the sign, right? It's the sign between the two pieces. Over here, it's subtraction. So we have a difference of squares. Over here, there's addition. So if I were to try to factor this in somewhat the same fashion, I might try to do something like this. The problem is if you multiply that back out, you don't get x squared plus 1, you get x squared minus 1. So this isn't the factoring for that. There is no way to factor that numerator because it's a sum of squares and not a difference of squares. It's kind of one of those things to be aware of. They change those signs around. So I actually don't have the ability to factor that numerator. Another way that you know that the numerator doesn't factor is what happens if you try to just plug in -1. On the bottom, you get 0. What do you get on the top? 2, right? Because I have to square the negative. So if I simply tried to plug in like this, I get 2 over 0. That also tells me that at least it won't factor at that point where it cancels the denominator out, which is the point of consideration right now anyway. So this is what we're ending up getting. And of course, this is no good in terms of like an actual value. 2 divided by 0 is not a number. It's undefined. But this tells me, right, this tells me that there's a vertical asymptote. And it's happening because the numerator, namely x squared plus 1, it doesn't factor at all. But for the purposes of what we care about right now, at the very least, it doesn't reduce. with the x plus 1 in the denominator. Does that make sense? So we have a vertical asymptote for that reason. And there's other kind of similar statements you could make that would be okay as well. All right. Last page. First, we're going to look at some more properties of limits. And you're probably thinking, like, haven't we done this already? And the answer is yes, we have, but not for infinite limits. So if it feels very similar, that's because it is. A lot of the things you're seeing happen again are going to happen again. But this is related now specifically to infinite values. So this tells us that we have C and L are real numbers, F and G are functions, and we actually have the limit of f of x is infinity, and the limit of g of x is L. So those are different pieces, right? Before, right here, I wouldn't have had an infinity. I would have had one of them is L and one of them is K. They were both numbers. So at this point now, one of them is an infinite limit, the other one's finite. So the first one's saying, all right, well, what happens when we add something that's infinite and something that's finite, or subtract something that's infinite and something that's finite? Well, if you have infinity plus a number or infinity minus a number, what's it equal? It's infinity, right? Infinity is bigger than any of those values. So that's the first one, sum and difference. The second one's similar, product. It's telling you that if you have the product of infinity with a number, it's also going to be infinite. So why is it showing with a negative infinity and a positive infinity? Well, it depends on what L is. Is L a positive number or a negative number? So if you have infinity times a positive number, you get positive infinity. If you have infinity times a negative number, you get negative infinity. And the last one, C, or 3, quotient, is telling you that if you divide a limit, L, right, just a number, by something that is infinite, you actually get 0. Right? So think about what's happening here. Just use an easy number, 1. So if you take 1 and you divide by something that's getting bigger and bigger and bigger, right? You have 1 divided by 10, and then 1 divided by 100, and then 1 divided by 1,000, and then 1 divided by 10,000, and 1 divided by, a billion, right? Like it keeps getting bigger. What happens to the number that you're getting?
It gets smaller and smaller.
It gets smaller and smaller. It gets infinitely small. And infinitely small towards 0, not towards negative infinity. But I go down towards 0. So you see something happening here, and we sometimes don't abbreviate it, and this is not a great notation, but if you have a number divided by infinity, it at least approaches 0. It doesn't equal 0, really, right? The limit equals 0. But if you have a number dividing by something getting infinitely large, it's getting infinitely small towards 0. Okay? And notice it doesn't matter whether it's positive or negative, and the reason is because 0 doesn't have a sign. Right? So if you're getting infinitely small towards 0 from above the x-axis, it's still approaching 0. From below the x-axis, it's still approaching 0, either way. Similar properties will hold for one-sided limits and for functions for which the limit of f of x as x approaches c is negative infinity. So we're not going to write this statement all out again and just change the limit that's in blue to say negative infinity and show what happens. If there's a similar argument, it's going to almost look identical. There's just going to be a sign difference on things. All right, so I promised you that we would do one with graph, which we did, and I promised you we'd do one with a table, which we're about to do. So this one is we're going to find a one-sided limit if it exists. You could do this with a graph, right? It doesn't say you have to use a table here. So if you don't have directions given that are told, if you're not told, use a graph or use a table, use graphical or use numerical, then you get to pick. I just want to show you one that has a table since I did one already that had a graph. Okay? So this one is the limit as x approaches 2 from the left of x squared over x squared minus 4. And notice if you do try to plug in 2 squared on top gives you 4. Okay? And then the 2 squared minus 4 on bottom gives you 0. So if we attempt to try to plug this in, we're going to get 4 over 0. And so this is going to approach either positive or negative infinity. It will be one or the two. I just don't know which. The question is which one. Okay? So we should have some anticipation of the answer here. It needs to be positive or negative infinity. So if this shows up and tells you that it's 7, you should have a red flag in your say that says that doesn't make sense. I was expecting it to be positive or negative infinity. So do I need to go back and reevaluate my expectation, and my expectation was wrong, or do I need to evaluate my work, and my work is wrong? Okay? So this will look just like the tables that we saw before. So we set up an XY chart, X on one, Y on the other, and we want to pick values that are approaching 2 from the left. What does 2 from the left mean?
Like slightly smaller.
Slightly smaller than 2. So somebody tell me a slightly smaller than 2 number that seems reasonable to start at.
1.9.
1.9 would work. And again, it's not the only thing that works, but it's a good place to start. And I want to have at least 3 values that get closer than 1.9. So I've got the 1.9. I want 2 more, I should say. So what else could I use? Yep. So these are 3 very good choices of places that we can go with. And we're going to use our table and our calculator to do this. So the last time we did the tables in the calculator, I didn't have my calculator with me, and so we kind of just walked around. So I want to show you how to do it in your calculator one more time in case you haven't had a chance to explore that yet. So you're going to take your graph of your equation of your that you're given, and you're going to put it into y equals. So the equation was x squared on top, and then mine forces me to put some parentheses. Yours may or may not. It may actually put it into a denominator, and you have x squared minus 4. So one way or another, your equation has to be into your calculator. If you're using a scientific calculator, that's fine. You're just going to enter these by hand. It's going to take you a little bit more in terms of keystrokes. So over here then, we're going to go into our table. Now in your table, this one is a really good example. If you can't plug a number in, like I can't right now, I can't put in 1.9, it just doesn't do anything. It means we need to adjust the table. And underneath the window button, it says table setup. Do you see a table set? So if you hit second window right here, you want the first one, the independent variable, to say ask. So your screen should say the table star at the delta table values, none of that matters. What matters is that the independent says ask and the dependent says auto. We've got to go ask and auto. And then if I go back into my table, I hit second graph, I have a completely blank screen. Or I might have a screen that has something in it, but I can type on top of it. So I can put in like the 1.9. Okay, is anyone not able to make their calculator show up like this at this point? Okay, so I'm going to put in the 1.99 and 1.999. The values that are showing up over here, the first one has 3 decimal points. It actually says negative 9.258. You should have at least 3 decimal points parts of your answer. I prefer more because I don't want to make an error in rounding later. So you can actually see more of them if you arrow over on top of the value, and it shows you at the bottom a more fleshed out description, right? I've got more decimals. So I'm going to put 6, 256, and then it's 410. So on my screen, I'm just writing all those down for us for later. And then if you arrow down, you can see the next one. And again, down at the bottom, it gives you more decimals. So I've got negative 99.2506 27. And then if I arrow down one more time, I get negative 999.250063. So this is what our calculator screen showed. And now it's written on our paper or it's on my screen. What value am I approaching as I go down this table? Right, It's negative infinity. So my answer, make sure you're giving an answer to the question, is negative infinity. The work is either this table, or, again, if you wish, you could do a graph like this for the problem, right? And show which part of the graph you're looking at. Here's the caveat. On this problem, the one that's on the screen now, number 1, we were asked to do the left-hand limit and the right-hand limit, correct? On the example 4 that we're doing right now, we're not asked to do both of them. We're only asked to do one. So the work better reflect which one I'm showing that I'm doing. So if you're going to draw this one, right, if you're going to do this from the standpoint of a graph, your graph would look like this. Something like this anyway. You're looking at 2 from the left, so 2 is here, and the 2 from the left would be these values down here. So you're not going to just go circling all the places where it goes up and down, right? We did that on the first one because we were asked 2 questions. Here we're only asked 1 question. We need to make sure that the part that we're looking at on the graph is the part that we're really trying to find information about. And it would be the green part that I've circled, because it's values that are close to 2 and slightly to the left. There's other places where there's infinite limits. There's other places where I have vertical asymptotes here, but the green part I've circled is the part that answers my question. Okay? All right, so there's WebAssign for this that will be due next class period before class. And then feel free to go ahead and start the review if you would like for the test that's happening on Wednesday.